Good morning, everyone. Welcome to this session. Our first speaker is Professor Wang from Institute of Atmospheric Physics, Chinese Academy of Sciences. Professor Wang is very famous. His research interests are climate system model, data assimilation, computational geophysical fluid dynamics, and he has published papers in some top journals of geosciences. The title of his talk is the DRP-4 variational data assimilation method, theory and applications. Let's welcome Professor Wang.
Okay, thanks for the chairman for the introduction of my research work, and I'm very glad to have this chance to share my research work here. My title is of the presentation is the DRP-4DVar data assimilation method, and include the theory and the applications. My talk include 4 parts. First, I want to tell about why we want to make data assimilation. Actually, data assimilation is the need of weather prediction and climate prediction. Sorry, I forgot. Actually, because the advances in observational techniques, and we have many platforms to real-time monitor the atmospheric state, including satellite, ground-based radar, and aircraft, ship, and balloons. However, these observations exhibit irregular distributions and different random errors. Because of their errors, observations are never be true. Therefore, we want to combine this observation to generate an optimal estimation of the truth within the regular spatial temporal distributions. This is why we want to do data assimilation. And data assimilation can provide such optimal estimation of the truth through incorporating multi-source observations based on a period estimation with regular spatial temporal distribution. In general, this period estimation is derived from a short-time forecast by the model. Here is the prediction. We want a numerical model. And this model includes the evolution law of atmosphere. And this model needs an initial condition. IC means initial conditions. So if the initial condition is not very good, and then the forecast will be not successful. So first, we want to get a high quality initial conditions. In addition, we also need a forcing, including the upper and lower bottom boundary conditions. And these three actually model plus initial condition and external forcing equal to the prediction. So how can we get a high quality initial condition? So we need a data simulation. So data simulation play an important role in the prediction process. We want to, based on a background from the prediction, and combine the observation and use data or simulation method to generate a high quality initial conditions, and then we make a prediction. This is why we need a data simulation. Actually, we know the parallel circuit. Here, we can note that in this circuit, the electric resistance can be minimized here. The more the ER and the more the last ER. And similar to this circuit, our data simulation also want to make the error to be the minimum here. And we even have a similar formulation here. You can see it's very similar. So PA is a method to parallelly combine various observations with the background to produce a high quality initial conditions. And finally, the DA analysis error variance will be the minima. This is the principle of minimal variance. This is one of the three DA series. So we can see that the error estimation is really important for DA. In a DA method, there are two kinds of errors, which are the background error and the observation error, because we want to combine these two kinds of data to make a high quality initial conditions. Therefore, accurately to estimate the errors is very important for increase the analysis quality and the forecast skill. In the background, there exist relations between different variables, or even the same variable at different locations. Therefore, background error covariance is considered in a DMS, not only the background error for each variables or each grid point. We want to consider the covariance. Means we should consider the relationship between the errors, different errors, which this background error covariance is usually expressed as a matrix, simply called B matrix. As for the observation errors, it is supposed that observations are independent each other, and thus only the observation error variance, not covariance, is taken into account in a data method. Existing DA methods include three aspects. The first one is the optimal interpolation. This method is based on the principle of minimal variance, just as I showed before. And the second one is the variational data assimilation family. This family is based on the Bayesian principle and maximum likelihood estimation. This method minimizes a cost function, very similar to AI to minimize a finite function. Two widely used members in this family is 3DVar and 4DVar data assimilation. Another kind of DA method is the ensemble DA. This method is also based on the principle of minimal variance. But this method does not minimize the analysis error and does not minimize a cost function. This method transmits and updates the uncertainties to accurately estimate the error, and it is development. In this family, a representative method is ensemble common field. Here is a picture for the 3DVar and the 4DVar. You can see that we can have a prediction trajectory. Here, if without the width, we don't make data assimilation. And then 3DVar is just make the distance between background and the single observation minimal. While the 4DVar can minimize the distances, the distance between the forecast trajectory and many observations, and as well as the background. So generally, 4DVar is better than 3DVar, especially this method contains the dynamic and physical constraint through the numerical model. Here is the ensemble common field. This ensemble common field has many members, and we can estimate the uncertainties, and also can update and transmit this uncertainty forward. DA is, as I mentioned before, DA is the need of numerical weather and climate predictions. Here is the numerical weather prediction. And here is a sub-seasonal to seasonal prediction, simply S to S. And another one is the decadal climate prediction. We want to make a 10-year lead forecast. And another one is the climate projection. This is different from the prediction because this is the singular is only from the boundary condition other than from the initial condition. Therefore, the rule of the DA is to provide high quality initial conditions for numerical weather prediction, H2S, decade climate prediction, and so on. Next, I want to introduce why we want to use DRP-4DVar. What is DRP-4DVar? Actually, this is a kind of a kind of 4DVar, but is very time-safe. Is more time-saving than 4DVar. We can compare three kind of DA method. This is the ensemble computer and 3DVar and 4DVar. Because the OI, optimal interpolation, is the only method here we want to compare it here. The red one is the advantage, and the blue one is the disadvantages. We can see here the ensemble compute don't need use the agent model, and so it is 10-7, and it is B matrix is flow dependent explicitly, means the B matrix can be can keep updating. But this B matrix usually may be underestimated. Another shortcoming is only single time observations are assimilated each time. This is for the ENKF ensemble compute. For 3DVar, have the same similar advantages. It does not use agent model and is 10-7, but the B matrix used in this method is static and climatologic. Also, only single time observations are assimilated each time. For 4DVar, although the B matrix is still static and climatologic, but it is flow dependent implicitly, but not explicitly. Especially, this method can assimilate multi-time observations each time. However, the agent model is required and high costs are needed. This is the shortcoming of the 4DVar. Overall, 4DVar is the most advanced data assimilation method currently. However, this method have the limitations. We summarized it, these limitations here. First, it requires the development of tangent linear and the agent model specific to the focus model, which entails high development costs, significant maintenance expenses, and non-update cycles. Consequently, its update pace can hardly keep up with the model upgrade. Second, the background error covariance matrix, simply B matrix, employed in this method is still the static and the constant matrix. Also, it is flow dependent implicitly. So this shortcoming may influence the performance of 4DVar. Because the first limitation, because need the agent model. In the world, only 6 national centers can have the ability to establish 4DVar DA systems, such as Europe Center, France, Met Office, UK, Met Office, and the Canada Development Center of Climate, Japan, and China. Even USA currently so far doesn't have the 4DVar system. This is due to the difficulty to develop an agent model. Especially because the second limitation, many centers, these centers have 4DVar system to have to hybrid the 4DVar and ensemble DA, so that the B matrix can be improved and can update and develop the B matrix. Here, the development tendency of DA include 2 aspects. First, the reasonable combination of 4DVar and ensemble-based DA, such as ensemble common field, currently represents the mainstream development direction of DA. This is the first one. And the second one, EN4DVar stands as one of the most representative approaches for reasonably combining these 2 methods. However, because EN4DVar wanted to run both the 4DVar system and the ENKF system, and it will take more computational resources. Therefore, another DA method called 4D-ENVAR, which uses pure ensemble error covariance to minimize 4DVar cost function, is paid more attention. For example, the DRP-4DVar means dimension-reduced projection 4DVar. This method is put forward by my group. DRP-4DVar is a kind of 4D-ENVAR. This method uses ensemble method to minimize 4DVar cost function instead of agent technique. Therefore, this method is agent-free and thus need no cost. Especially the analysis consistent with model constraint and similar to 4DVar. The cost function is the same as the 4DVar here, but in another form, the incremental 4DVar. And here we need some samples. Here we call the ensemble samples. Generally, this the size is not very large. Generally, is is under 100. So it's not similar to the AI need a larger size larger number of samples. Here we only many few numbers can train a agent model and engineering models. However, limited samples to estimate B matrix may lead to some shortcoming. First, the rank of the B matrix is deficient, and another there are some spurious correlations. So we use a technique called localization to increase the number of samples. We expand the correlation matrix. We get the leading model, and then we can produce many extended samples based on the original sample. So in this way, we can solve this problem and also save the time. And the second part is the third part is the application of our method. The applications include 4 parts. First is the regional mesoscale weather prediction. We just give the simple examples. The first example is the heavy rainfall in actually should be 2006 in the year. Here is the control experiment. Control experiment means we make a forecast without data assimilation. We didn't combine the observation to the forecast. This is a control experiment. Another experiment is the forecast with DA, but use our method DRP-4DVar to combine the observation. The second one is the third one. The third experiment is the forecast with DA, but use the standard 4DVar, the traditional 4DVar, to assimilate the same observations. I think I missed some information. Yeah. Oh, I'm sorry. And we can see that both methods, DRP-4DVar and agent-based 4DVar, can reduce the lumen square error here, no matter for 24-hour forecast and 48-hour forecast here. And we can, two methods can all reduce the errors. we can see the spatial distribution of the errors. Here is the control minus observation. This is the DRP-4DVar minus observation, and this is agent-based 4DVar minus observations. This is a 24-hour forecast. You can see that without data simulation, the errors is very obvious. And when we use the data simulation to incorporate incorporate the observations, we can see that the errors are reduced very significantly. And we can see that both methods have the similar performance. Another example is the typhoon forecast experiment. We use data simulation to prepare initial conditions for the typhoon forecast here. And this is a typhoon occurred in 2009, named Ninfa. And here is the observation, the black line. And this one is our forecast. Use the DRP-4DVar to incorporate two kinds of data. One is the conventional data observation, and another is the box data. And we can see that the forecast is very close to the observation, and the track error is smaller than other two forecasts. So we can see our DA method can have good performance on the massive scale weather forecast. The second application is the global medium range forecast. This prediction have a time scale from 1 day to 10 days, generally 10 days, or even to 2 weeks. So generally we have to use a global model rather than the regional model. Here, CMA means China Meteorological Administration. GFS is a global forecast system. Is an operational forecast system in CMA. And we use this operational model established the DRP-4DVar DA system. Actually, in CMA, there is a 4DVar system, and we based on this system, and then we established the DRP-4DVar system. The red one is the new component we added to the system, and then established a complete DRP-4DVar system for CMA GFS. First, we compare the performance on DA analysis with the ENKF, ETKF, another kind of ensemble DA, similar to ENKF. And the green line is the null line. Here is 0. And the red one is the difference of errors of two methods. Here is the ETKF minus 4DVar. Therefore, if the red line have the positive value, means the error of ETKF is larger than DRP-4DVar. You can see that all the red line almost have the positive values, means DRP-4DVar have a better performance than the ETKF. And then we also compare to the original 4DVar system. You can see here is North Hemisphere, South Hemisphere, East Asia, tropics, 4 regions here. And the solid line means the analysis, DA analysis. And the dashed line is the background, the post gas. And the black one, the black line means the 4DVar analysis, and the red line is the DRP-4DVar analysis. You can see that in the left means the error is smaller, and on the right side, the error is larger. And you can see that the red line always in the left of the black line. So it means the analysis quality of DRP-4DVar is better than that of the traditional 4DVar. Especially our method is very tense-saving. This is the analysis quality. And for the forecast, 1 day to 10 days, this one is correlation coefficient, and this is no mean square error. The pink there means worse, and the green triangle indicates better. You can see that almost for almost the variables and lead forecast days have the green triangle. So generally, the forecast scale based on DRP-4DVar is better than the forecast scale for traditional 4DVar. So we can see that the analysis quality and the sample mean forecast scale of DRP-4DVar is better than those of traditional 4DVar. This is the second application of DRP-4DVar. And the third application is sub-seasonal to seasonal prediction. Actually, this is a very difficult task to make a so long predictions. We have a gray zone just between the 2 weeks to 1 month. Actually, we currently all prediction models in the world have no scale in this period, in this gray zone. So this prediction try to increase the predictability in this zone, gray zone. For the sub-seasonal to seasonal, we have to use a coupled model rather than a single atmospheric models, because in this time scale, there are IRC interaction and other multi-component interactions we should be considered. And to make the S2S predictions, we use a coupled model called F equals G2. This model is also developed by our group and is one of the CMIP models. CMIP means an international project is a coupled model intercomparison project, fifth phase. And this model in CMIP 5 shows very good performance in the intercomparisons. And the initial condition for the coupled model is also use the DRP-4DVar approach. And then we established a coupled data assimilation system. Actually, coupled data assimilation system is different from the single model data assimilation system, because we have to consider the multi-component interactions in the DA system. Here is the coupled model. We use a coupler to combine multi-components, including atmosphere, ocean, land surface, and sea ice. And then we can consider multi-component interactions here, especially the IRC interaction. And then we add a component to the coupler. This is a DA component. Use the method by ourselves. That is the DRP-4DVar. And we have many papers published about the DRP-4DVar and even about the coupled DA system. Currently, we connect this component to atmosphere, ocean, and land surface. And this part is ongoing and have not completed currently. And first, we use this coupled model and our DA method to make S2S predictions. Here we show examples here. The first is the 40-day need forecast. Actually, this is very hard, very difficult to make a 40-day need forecast. In your center, the forecast is effective only before 10 days. 10 days. So for 14-day need forecast in this time is in the gray zone, so it's very difficult to make. And here we make a 40-day forecast for the monsoon on site. And we can hit the source east window here. And according to the National Climate Center's monitoring on May 30, 2024, the South China Sea summer monsoon onset occurred in the 6th pentad of May, specifically on May 26th. And our result indicate the establishment of southwesterly winds at 850 100 par from May 22 onward, suggesting the South China Sea summer monsoon onset is highly probable within this pentad. So the prediction is very close to the observation. And here is the tropical cyclone typhoon forecast. Here we don't want to predict the track and the intensity. We just want to prediction it is genesis. You can see that we made a 16-day leader forecast for the typhoon genesis. The predicted genesis date is on the May 24, 2024. This forecast is consistent with the ensemble forecast in Europe Center. And the observation show the actual genesis time is just on the same day. So our 16-day lead forecast is consistent with the observation. The last one is for the 3 months. 3 months forecast of the heavy rainfall during the flood season. Our forecast successfully captured the observation through major dry regions across China. Here. The observation is here. So we accurately captured the dry 3 major dry regions, but we failed to capture the wet region very well. So we have to continue to improve the DA system and the model system. And the last application is decade predictions. Actually, decade prediction is very difficult. For example, for a internal variability at a decade scale is the PDO, Pacific Decade Oscillation, this variability significantly influence the monsoon in China in the decade scale. You can see that the model in the world is very difficult to make accurate predictions in lead time rather than the 3 years. You can see very few models have skill in the 3-year forecast and longer forecast. Especially, no models can have a good performance in each year forecast. And you can see that the scales of predictions 3-year or longer in advance are generally low. Most this is the confidence level here, and most of the predictions is under this level. And we design an experiment. First, we have a long-term data assimilation, means initialization, from 1945 to from 1996, and we make 10-year forecast here. Actually, they are the handcasts, and we have 10 members. And then we can see that the red cycle, the red 4 cycle is our forecast. So we have very good performance at each lead time. You can see 1 year, 2 year, 3 year, and 10 year. Especially the 10-year mean is much better than other decade predictions in the world. So we can see that a good data assimilation method can lead to very high prediction scale for decadal climate prediction. Finally, we make a summary and give some discussions. The DRP-4DVar actually uses limited ensemble samples to train a linear transform from initial perturbation to observation innovations, and thus need a non-agent model. So it's 10-7. Actually, this idea is very similar to AI to train a model. And also it updates the background error covariance at each assimilation, so that the B matrix is flow dependent both explicitly and implicitly. Okay, miss I. Yeah, I'm sorry. And second, the application of DRP-4DVar indicate that this method improves meso-scale weather forecasts, such as heavy rainfall and typhoon track. And it has higher analysis qualities and better ensemble mean forecast scale than 4DVar. And it has good performance on S2S predictions including monsoon onset, typhoon genesis, and rainfall in flood season. And especially it significantly improved the decade prediction of PDO compared with the same prediction by CMAP5 and CMAP6 models. And finally, we have a discussion. Actually, our method is very similar to AI. So how can we combine the AI technique into our method to further improve his performance? So this may be an interesting topic in this field. And also, 4DVar minimize a focus function. Why? AI minimize a finite function. However, the 4DVar minimization needs no samples. And so, can we find something for AI minimization? Maybe can reduce the number of samples in AI according to the 4DVar minimization. Thank you. This is my talk.
Thank you, Professor Wang. Very interesting. Any questions?
So we learned about the breakthroughs from like 3DVar to 4DVar and from 4DVar to DRP-4DVar. So I'm curious about like what specific research steps we did to improve this kind of limitations. Like in other words, like what you actually did and think when you face this kind of difficulties.
You mean from the 4DVar to DRP-4DVar?
Yeah, like from different methods and different models. So what we did to make this better, things like that.
Yes. Actually, no matter the traditional 4DVar and our DRP-4DVar can use it on different models, especially different forecast and weather forecast model, climate model. So no problem.
Yeah, I mean, so how do you improve this kind of models? How do you improve this kind of methods from 4DVar to like DRP-4DVar? 可以说中文。就是有什么具体的研究步骤，去精进这些不同的从4D 或者 DRP 之类的东西，就是具体在这几个精进的方面做了些什么？
I don't understand you mean 你是什么意思？我还
就是我比较好奇，
就是
我比较好奇从就是4DVar 到 DRP-4DVar 这两个东西之间，就是具体的做了什么，才能让他们更加的精确之类的？就是怎么进行这个研究的？
Okay. Actually, currently we have really the choose. So it's very difficult to estimate the errors of forecast and observation. Many people regard the observation as a truth. Actually, no. Sometimes the errors of the observation are even larger than the forecast errors. So observations are never the truth. So we try to combine the forecast and observation to generate a more accurate data. And this data is more close to the truth.
所以就是通过改进数据来做更好、更精确的这个预测。
对。 Yes. The
Okay,
initial
thank you.
condition is very important for a prediction, no matter weather prediction and climate prediction. So the accuracy of the initial condition is very very important. 你可以想象，如果初始状况不准确，这个模式再好也预报不出来了。
Okay, thank you.
Thank you. Any questions? I have a question. What is the specific model in use?
你说那个 forecast model 是吧？就是实际上我们这个预报目前都用的是基于流体力学方程建立的模型了，但是还有一些次网跟尺度的那个过程，然后比较人为，所以这个里面可能 AI 可以发挥很大的作用。对算力，我们的实际上就是实际算力有了啊，但是要做批量的，比如说我们刚是一个 case 不行了，是要连续1个月甚至连续1年的这个预报结果才有统计意义，是这样的。
Okay. If there are no other questions, let's thank Professor Wang again. Now we can take a short break for 10 minutes.